video, I'm going to be going through hydrogen fuel cells and greenhouse gas confusion, why batteries stop working, and then going through the titration calculation, our limiting reagent calculations, and our volume of nitrogen question. Just wanted to flag up from that 6-mark question, it was a lot of us weren't bringing in our own knowledge, so we were using the information in the table, but we weren't using our own knowledge or giving a judgment. So you're going to give you a new 6-mark question that requires the use of a table and own knowledge in order for us to further develop that practice. You'll then have from your emails 2 recommended areas for improvement and activities to follow in the PowerPoint to help you improve those areas. Reacting with water to form hydroxide ions. So these are half equations because they're happening at different electrodes. So we need to balance them and also think about the electrons that are involved. So on my left hand side of my reaction I've got 3 hydrogens, but on my right hand side I have 2. So I'm needing to increase my numbers of hydrogens on my right hand side. So I now have 4 on my right hand side, but still only 3 on the left hand side. So now I need to increase my numbers of hydrogens on my left hand side. So to do that I've increased my number of hydroxide ions. So I've now got all my elements balanced, however my charge is not balanced. On my left hand side I have an overall charge of -2 because 2 lots of the -1 hydroxide ions, and so on my right hand side I need the charge to be the same, so it's going to be +2 electrons to give that -2 charge on the right hand side as well. With my oxygen half equation I have 3 oxygens on my left hand side, but only 1 on the right hand side. I also have 2 hydrogens on this side, so if I were to make that 3 I would have 3 hydrogens and that wouldn't balance nicely. So what I'm going to need to do is make this 4 hydroxides, so I now have 4 oxygens, and on this side I only have 3. But if I make this 2 waters, I then get my 4 hydrogens and my 2 oxygens. Charges on this side is -4, but on this side it's 0, so I'm going to need to add some electrons on my left hand side in order to make the charges the same on each side. And so I'm going to need 4 electrons in order for it to be a -4 charge on both sides. My overall equation is going to be 2H2 plus O2 goes to 2H2O. So my only product from this is water. So water, it is actually a greenhouse gas, and we're going to look at that in our next topic. But a lot of us in our answers were saying that it doesn't produce any greenhouse gases. That's actually incorrect, because water is still a greenhouse gas. However, we do describe it as being clean, as no carbon dioxide is produced. So it is still advantageous because we don't have the carbon dioxide being produced. However, it is a greenhouse gas. So we just need to be careful in our answers as to how we're describing that clean production of our product. So there's no carbon dioxide produced, so it's a clean energy source. However, our greenhouse it is still a greenhouse gas. We should also note that hydrogen is non-renewable. As a disadvantage of this. So obviously there is a finite amount of hydrogen, and so it isn't a renewable resource. The next thing to talk about is batteries. So we have two types of cells. We have primary cells and we have secondary cells. Now, our primary cells are non-reversible, whereas our secondary cells, they are reversible reactions, and therefore they are rechargeable, whereas our non-reversible reactions are non-rechargeable, as we can't go back to the original battery state. However, in both of these cases, what stops a battery from working is when one of the reactants is used up. Or like the reaction is completed. So in both of these cases, our battery would stop working. For our primary cells, we'd need to recycle those, but for our secondary cells, we would then need to recharge those. So that's happening when one of the reactants is used up or the reaction has been completed, so you can't have any more of that reaction happening, and therefore the battery isn't going to be working. Okay, so turning now to our titrations questions, so questions 5 and 6. So question 6 was about the equipment that we were using, so why we should use a pipette to measure the dilute sulfuric acid and a burette to measure the sodium hydroxide solution. So in the question they've specified that they are using 25.0 centimetres cubed of sulfuric acid, and then we are measuring the volume of sodium hydroxide required. So this volume is a fixed volume, and so that is why we use a pipette, as pipettes come as a fixed size, so there is only one line, and that is for the specific volume. So using a pipette in order to get a specific fixed volume of an amount of solution, whereas here we're going to be measuring the volume that we're using. So this is why we would use a burette, because we're going to have a variable volume that we are adding to the solution. So we're using a burette to do this. As with our burette, we can use the tap in order to add our solution to the conical flask, and then we've got multiple lines, and so we can measure multiple volumes. And the point of this experiment is we don't know how much sodium hydroxide we're going to need, so we're needing to have that variable volume to be able to measure. So it could be 24, or it could be 23, or it could be 10. We don't know, and that's why we're using the burette, is in order to measure that volume. But it could be any volume within that range. Okay, so now turn to the calculation part, so question 5. So we're going to be calculating our concentration of sulfuric acid in moles per decimeters cubed. They've asked us to only use the concordant results and that they are results within 0.1 of each other. So titration 1 was 23.5, titration 2 21.1, titration 3 22.1, 4 was 22.15 and 5 22.15. So our results that are within 0.1 of each other are these final three. So 22.1 is only 0.5 difference from the titration 4 and 5. So we can work out the average volume of sodium hydroxide and that would be 22.1 plus 22.15 plus 22.15 divided by 3. And so we get an average volume of 22.13 centimetres cubed. They've given us the balanced equation for this. So 2NaOH plus H2SO4 goes to Na2SO4 plus 2H2O. So this balanced equation tells us our ratio of moles of sodium hydroxide to moles of sulfuric acid. So it's a 2 to 1 ratio. Remember that when there isn't a number in front of a molecule, that's because it's just 1. And we want to remind ourselves of our concentration, what it is. So how concentrated something is telling us how much of something there is in a given volume. So in this case we're working in moles and our volume we're wanting in decimeters cubed. We have a volume in centimeters cubed, and in order to convert to decimeters cubed we need to divide by 1000, so we get 0.02213 decimeters cubed as our volume of sodium hydroxide. So our three variables that we're looking at is concentration, our moles and our volume. So we need to fill in information that we've got from our question, and we know that our unknown, what we're trying to find out, is this concentration of sulfuric acid. But we know that our volume of sulfuric acid was 25 centimeters cubed. Convert that into decimeters cubed by dividing by 1000 and we get 0.025. And we know our concentration of sodium hydroxide is 0.105, and we've just worked out that the volume that we used was 0.02213, and so by using this we can work out our moles of our sodium hydroxide, which is going to be twice the number of moles of our sulfuric acid. And then once we have our moles of sulfuric acid and the volume that it's in, we can then work out our concentration. So our moles of NaOH can be given by our concentration times our volume in order to get our moles. So that's going to be 0.105 times 0.02213. 0.0023224 moles, and so then our moles of sulfuric acid is going to be that divided by 2, which is 1162, and then now that we have our moles, we can work out our concentration of H2SO4, which is our moles of H2SO4 divided by our volume of H2SO4. So 0.001162 divided by 0.025, and it's 0.046 moles per decimeter cubed. Okay, so this next question is our limiting reagent question from the assessment. Please also note it says you must include calculations in your answer. So if you got the correct limiting reagent but you didn't show your workings, we can give you the full marks as you hadn't shown your calculations. Equally, some of you had done part of the calculation, but there's a crucial step, which I'll highlight when I do it, that you needed to have included to show that it was the limiting reagent. So first things first is working out our moles of butane. So remember, moles equals mass divided by mR. We've got our mass of 14.5 grams from our question, and we can work out our mR of butane, which is C4H10. So we're going to have 4 lots of 12, as that's our atomic mass of carbon, plus 10 lots of 1, as that's our atomic mass of hydrogen. That comes out to 58. So our moles of butane we can get by doing 14.5 divided by 58, which comes out to be 0.25 moles. So then, looking at our question, 2 to 13 ratio, so our 0.25 is worth 2 parts, so 13 parts is going to be 0.25 divided by 2 to get 1 part, and then times by 13. So that comes out to be 1.625. So now we need to find out how much oxygen we have to then establish which our limiting reagent is. So our moles of oxygen is our mass divided by our mR. Mass we've got from the question, 72.0 grams. And then our mR, remembering oxygen is diatomic, so 2 lots of 16, 16 being the atomic mass of oxygen, but remember it's O2. So then our moles of oxygen is 72.0 divided by 32, and this comes out at 2.25 moles. So then this is our crucial step here. So 2.25 is greater than that 1.625 that we needed of the oxygen in order to react with all that butane. So as the amount of oxygen we have is greater than the amount of oxygen we needed for this amount of butane, our oxygen is in excess, and therefore butane is our limiting reagent. So we must have calculated the 1.625 and compared it to the 2.25 in order to get our full 4 marks. Okay, so question 13 was looking at our volume of nitrogen gas. So they've said that 1 gram of nitrogen has a volume of 0.86 litres at room temperature and pressure. In question 12 we were working out our mass produced from 130 grams of sodium azide, and so we're after the volume of that mass of nitrogen. They've given us a mass of 80 grams if you hadn't been able to work out what the answer for the previous question was. However, our mass was, to 2 significant figures, 84 grams. So if we have times our mass by 84, then in order to get our volume, we're going to be timesing that by 84. So it's one of those scaling relationships. So our volume is going to be 0.86 times 84, as we've got 84 times the amount that we had at the start, and that comes out to be 72 litres to 2 significant figures.